Welcome back to the morning show. Something huge happened in the world of physics yesterday, and it was above our heads.
Literally, wise guy Paul Kwiat shares how to see a black hole in today's Wise Guys Wednesday.
Hey everyone, nice to see you again. Today we're going to do a bit of a topical episode based on some big news that happened yesterday. Some of you might have heard about it. But first, let's just try to make a connection with something that we're certainly familiar with. So if I have an object and I throw it up in the air, of course, it's just going to come right back down. Of course, if I throw it harder, it's going to take longer to come back down. And if I could throw it hard enough so that it can actually climb up the gravity well of the Earth, basically it can escape from that, then it can go off into orbit, go off into space. And pretty easy to calculate to show how fast it needs to be going in order to do that. So the escape velocity is given by this pretty simple formula. The exact details don't matter, except that we see that as the mass of the Earth gets bigger, then you need to go faster, and as the radius gets smaller, then you need to go faster. So if I look with calculate this for the Earth, for example, with its mass and its radius, I'll find an escape velocity of about 11,000 meters, 11 kilometers a second, or 7 miles a second. That's how fast a rocket needs to be going when it leaves the Earth in order to be able to completely escape and go off into space. Now, if you could imagine that I could take the radius of the Earth and make it a lot smaller, basically take all the mass and compress it, well, what that's going to do, if I make the radius smaller, is the escape velocity is going to go up. And in fact, if I could take the entire mass of the Earth and get it to be in something that's only about an inch across, a little less than an inch across, we find that the escape velocity then would be 3 times 10 to the 8th meters per second, or 186,000 miles a second. And hopefully some of you might recognize that, might ring a bell. That's actually the speed of light. So that's the fastest that anything can go. And when you can get something so it's that dense, then we have a black hole. So a black hole is an object that is so massive, usually something like many masses of a star, so massive that the escape velocity is the speed of light, so that nothing can escape from it, not even light, which is why it's called a black hole. And in fact, this was in some way predicted by Einstein's general theory of relativity back in 1917, as sort of a numerical consequence of it. But even he didn't really believe that the black holes could actually somehow come into existence. And that brings us to the story of yesterday, which is the Nobel Prize in Physics was awarded to 3 scientists who were studying black holes. So the first of those was Roger Penrose, and he got the Nobel Prize basically for a theoretical discovery showing that black holes, in fact, form naturally as once you have the general theory of relativity, Einstein's theory of relativity. Black holes are just a natural consequence of that, although certainly not an obvious one, which is why he got the Nobel Prize. Okay, the other 2 Nobel Prizes in physics went to Reinhold Genzel and Andrea Ghez for discovering a supermassive compact object at the center of our galaxy, basically a black hole, what they believe to be a black hole. And maybe I'll just put a personal touch on this. So I actually know Andrea Ghez. We were both undergraduates at MIT together a long, long time ago, and quite significant because she's only the 4th woman in history ever to get a Nobel Prize in physics, which is a shame. I mean, it's great that she got it, but certainly more are on the way, hopefully. So what did they actually do? So how do you see something that's black? It's a little bit difficult, right? Because that's what it means is black. It doesn't reflect any light, like my face is reflecting light. If it doesn't reflect any light, how do you actually see it? And the way that they're going to look for it is they're going to look at other stars that are orbiting, in this case, this massive object at the center of the universe. And the orbiting velocity, very similar to the escape velocity, just a missing factor of 2. And so if you can see stars that have very large orbiting velocities, that must mean that you have a big mass and a small radius, which is exactly what we mean by a black hole. But there's something that makes this a little bit more difficult to see, which is that if you look toward the center of the galaxy, it's kind of like looking into this whole mass of lights here. It's not easy to see anything because there's all these stars, and to be able to track exactly how they're behaving, you have to have very precise telescopes. And there's one more thing that makes that tricky, which is that we have turbulence in our atmosphere. So if I look at a distant star, the light is just coming off in spherical waves. So by the time they get to us, they should be very smooth. They should look very nearly flat. But when we come through the atmosphere, they get distorted by that. The same reason that the stars twinkle at night, the waves are being distorted. And what the people who got the Nobel Prize did was they bounced this off a so-called an adaptive mirror, an adaptive optic, which is set to have exactly the right anti-distortion, so it completely compensates the distortion of the waves coming in. And they have to do this about 1,000 times a second. But when they do that, then they're able to go from things which normally look very distorted to things which can have extremely precise images. And with doing that, they were able to then see that some of the stars really whip around at extremely high velocity near the center of the galaxy. And from that, they can conclude that there's this very, very massive object. Okay. So just wanted to bring you up to date on the latest in physics, the Nobel Prize announced yesterday. I hope you guys all have a great week. Bye-bye.